Hello and welcome to a Chapter 7 practice problem. The problem we will be looking at today is similar to question 17 in Chapter 7, finding the standard error in multiple cases. The problem we will be dealing with today is suppose a random sample of 52 is selected from a population with a population standard deviation of 9. It is our job to find the standard error in each of the following cases, and we also must remember to use the finite correction factor when it's appropriate. So the situations we will be looking at today include the assumption of an infinite population, a population of 50,000, a population of 5,000, and a population of 500. So before we start the problem, we need to define our terms. We have n, which is our sample size, of 52, which is given to us in the problem. We also have sigma, our population standard deviation, which is 9. Now that we've defined our terms, we need to find out if our data is normally distributed. In this kind of a problem, we don't necessarily have to figure out whether our data is normally distributed, but it's good practice for the future. There are 3 ways we can do this. The problem will tell us that the data is bell-shaped and sigma is given. That's our first proof. The second proof is n is greater than or equal to 30 and sigma is given. And the final proof, the third proof, is n is just greater than 100. In our case, our proof is that n is greater than or equal to 30 and sigma is given. Once again, we don't necessarily have to do that for this problem, but it's good practice. So now the formula that we're going to be using today is our standard error formula of sigma divided by the square root of n multiplied, if we can, by the finite correction factor, which is the square root of capital N, our population, minus little n, our sample size, divided by our population, capital N, minus 1. We are allowed to use the finite correction factor if our sample size is greater than 0.5% of our population size. If we can use the finite correction factor, it will decrease our standard error, which allows our sample data to better represent our population. It is a reward for taking a large sample size of our population. So for our first part here, we are assuming an infinite population. I left the formula for standard error in our terms up in the top right corner in case you need to refer to it as we go. It will also be there for the other parts as well. So before we go any further into this, are we allowed to use the finite correction factor in this case? Take a second, pause, and try to see if you can figure it out if you can. Well, as it turns out, no, we can't, because we cannot use the finite correction factor here because we are not given a population size. It's very hard to figure out if 52 is greater than 5% of infinity because we just can't. So in this case, we cannot use the finite correction factor. So that being said, when we use our standard error formula, we are only allowed to use sigma divided by the square root of n, which gives us 9 divided by the square root of 52, which gives us a standard error of 1.2481. Moving on to our second part here, we are assuming a population size of 50,000. Now once again, before we go any further, are we allowed to use the finite correction factor here? Well, once again, no, we're not, because this time we can actually check, and it turns out our sample size is only 0.1% of our population, which means that our sample size is not greater than 5% of our population, so we cannot use it. So once again, just like in part A, we have to only use the first part of the formula, which gives us again 9 divided by the square root of 52. Which gives us the same standard error as in part A of 1.2481. Now moving on to our third part here, we're assuming a population size of 5,000. Now, once again, before we go any further, are we allowed to use the finite correction factor? Well, once again, we're not allowed to use the finite correction factor because the sample size is still not greater than 5% of our population. We can check that by taking 52 divided by 5,000, which gives us 0.0104, or roughly 1.04%. So once again, we're not allowed to use the finite correction factor. So when we use our standard error formula, just like parts A and B, we're only allowed to use the standard deviation sigma divided by the square root of n, which once again gives us 9 divided by the square root of 52, which gives us the same standard error as parts A and B of 1.2481. Now, our last part here, part D, we are assuming a sample size, or not a sample size, sorry, a population of 500. And once again, I'm going to ask you, are we allowed to use the finite correction factor? Well, as it turns out, this time, yes, we actually are allowed to use the finite correction factor, because when we check if our sample size is 5% or more of our population, or greater than 5% of our population, sorry, we can take 52 divided by 500, which gives us 0.104, which equates to roughly 10.4%, so we are greater than 5% here. So now we can use the entire formula, including the finite correction factor, which gives us sigma divided by the square root of n of 9 divided by the square root of 52. But we multiply that by the square root of 500, our population size in this case, minus our sample size of 52. And then we divide that by our population size of 500 minus 1, which will reduce our standard error. You'll notice that it's lower, because in this case, our standard error is 1.1826. So because we got to use the finite correction factor in this case, we were rewarded with a smaller standard error, which means that our sample size in this case, in part D here, represents the population better than they did in parts A, B, and C. I hope this video was helpful in explaining this concept to you, and I will see you in the next video.